Greetings. In this particular video, I'm going to explain how we can solve an ungate digital logic problem by using neural networks. So what is necessarily an ungate? Let's see its truth table, which is actually very normal, where we have two inputs, say 0, 0, the output will be 0. 0, 1, output will be 0. 1, 0, the output will be 0. Meaning like if any one of the input is 0, the output will be 0. If both the inputs are 1, the output will be 1. So this is AND gate with two input problem. Now the first question that comes to our mind is why a neural network way or an approach is required to solve this particular digital logic problem. Usually a neural network, either you call a perceptron or a multiple layer neural network, where you have inputs and outputs with some hidden layer between. And this AND gate is also having such a logic. Say, for example, the basic AND gate and the mathematical expression. In mathematics, 0 plus 0 you call 0. In AND gate, also it is 0. In mathematics, 0 plus 1 is 1. But in AND gate, 0, 1 is 0. In mathematics, 1 plus 0 is 1. But in AND gate, 1 plus 0 is 0. Here, 1 plus 1 in mathematics is 2. But in AND gate, 1 and 1 is 1. Usually, AND gate is compared with multiplication, but generally in neural networks, everything as input will be first undergoing a summation followed by some activations. So this particular AND gate is also compared with a summation of a neural network, neuron, where some activation need to be done so that the AND output should be obtained, where if two inputs are there, if any one is 0, output should be 0. If both are 1, output should be 1. So this is why we want to relate AND-gate problem to a neural network. And to be more clear, in one of our previous videos, we have seen XOR problem and said XOR is a non-linearly separable problem. But AND-gate is not such a complex problem where if you plot the inputs of AND-gate like 0, 0, 0, 1, 1, 0 and 1, 1, you see like 1, 1 alone, which is actually stated in red color over here, is what representing the output 1, but all others are 0. It is easily separable by using a linear line of some equation, say y is equal to mx plus c, where 1 comma 1 can be separated from rest of the inputs, which is going to give the output as 0. So this is an easy problem which is linearly separable, but a small condition that there should be a difference between a normal mathematics and the AND logic. So for that, we use something called as bias in neural network. And to solve this problem, we set the bias as 1, and we also assume that 0 to be called minus 1 and 1 called plus 1 in this particular problem, where minus 1 means a neuron is not fired and plus 1 means the neuron is fired. So what is the firing thing is the neuron is going to get activated so that it functions in such a way that its contribution is reflected in the output. So now if you see the updated truth table for the inputs of AND gate, we have minus 1, minus 1, minus 1, 1, 1, minus 1, 1, 1, wherein 0 is replaced by minus 1. And I'm setting the initial bias value for all the inputs to be 1. And I'm setting the output value as same, wherein 0 is actually replaced with minus 1. Now each of the inputs need to be handled separately. Since you have learned deep learning to an extent of optimizations, you know that each input is going to be handled separately, will come under stochastic gradient descent problem. Now we have to train the weights of x1, x2 and the bias term for modeling the AND gate. So now I'm using the Hebbian learning rule, the Hebb rule, where the new weight will be calculated as old weight plus the input and the output neuron, which are interlinked to each other. Now in the initial weight, I'm substituting the weights as 0, 0, 0. So I'm going with the new weight is equal to the current weight is 0, 0, 0 plus the current input I have is minus 1, minus 1, 1. So this is what the current input and the current output is minus 1. So this is how I actually move. So now in case if I want to increase the weights, it is always the user perspective where you can actually take on any particular weight and use it. But it is always recommended that you use initial weights as 0 so that it will not cause any influence in the later stage of the problem. Now I am having the initial weights. I'm using transpose here to ensure that this is a matrix and need to do multiplication in this particular term with a scalar value. So to aid this particular multiplication, I'm transposing the higher dimension so that matrix multiplication problem will not occur. And after multiplying with -1, I get this particular value 1, 1, -1, which upon addition with 0, 0, 0 will get me this particular result. Now, this is my updated weight in iteration 1 obtained through the input 0, 0, 1, or instead of 0, it is -1, -1, 1. Now, going for iteration 2, I can use the updated weights from iteration 1, which are 1, 1, -1. That is, the result of this is used here. So, this is how the weights are being updated. Now, when I'm taking the particular weights into consideration, the one thing which I can actually do is the initial weight setting should be periodically updated so that results also get updated. So I'm just getting the results. Now I'm moving on where I'm taking the next inputs. My next inputs here are -1, 1, and 1. So this is how my next inputs move. And for that as well, my output is -1. So with this, what we can actually go is we can actually take the values which is actually taking the inputs of the current iteration with the updated weights. Now let us go like how this particular weight updation is being calculated. Now I'm taking the -1 being substituted for multiplication term. I'm getting the updated weight value as 20 -2. In the similar process, I'm going for the next input value, which is 1 -1 1. I'm taking this particular value and -1 as the output. Just to substitute here with the updated weight. My updated weight is 20 -2, which is substituted here as 20 -2. Then I take the new input, the third input into consideration and its own output. Do the multiplication, add it, you'll get the new weight. Finally, we have only one more input left and taking this particular updated weight with the final input 1, 1, 1, wherein the output is also 1. If you substitute the final updated weight after all the iterations having all the inputs, you will get 2, 2, -2. Hence, AND gate in neural networks is solved with weight 1 for input x1 as 2, weight 2 for input x2 as 2, and bias weight for the term initial bias being 1 is -2. So if you use this particular term, it is ensured that the neural network structure can solve the AND gate problem. Hope this is understandable. We will see how we can use neural networks to solve other digital logics in the upcoming sessions. Thank you.